Welcome to Manifested Publishers. We offer CASNEP study materials and video lectures.
Hello, I greet you all. My name is Mr. J.M. Kimani. I welcome you to Lesson 5 of Topic 7, which is Decision Theory. Lesson 5 focuses on still game theory, but the graphical method. Now, in the previous lesson, lesson 4, we were having a question which I showed you how to determine the optimal strategy and also the value of the game using the algebra method and the probability method. Now, we are going to look at the graphical approach, graphical method for the same. So this is the same question, Kamau and Koech, then with their respective strategies, which is head, tail. These were the payoffs. Now, when you are solving graphically, so we normally have these. So these are the procedures. So we say let y represent expected value to come out. So the player on the sides. Then x represent probability of Kamau playing head, while 1 minus x representing probability of Kamau playing tail. One thing to do or to know with the graphical is that we cannot address the two players at the same time. We only address one player. And because this is a zero-sum game, one player is enough. If we get him losing, then we can be sure that the player is going to gain. If we have him gaining, then we can be sure the other player is going to be losing. Now, I've used the variables x and y because on the graph I'm having the y-axis and the x-axis. So on the y-axis, so I'm going to have the value. So therefore, y would represent the expected value for this Kamau, while x would represent the probability of Kamau playing head. That's what we'll be having. So since we have the two axes. Now we'll have this way. This is when Koech plays head, semicolon. So when Koech plays head, look at Koech now. Koech is here, playing head. The values for Kamau is either minus 50 or 40. And since we have the probability for head and tail, which is x and 1 minus x, we'll indicate here that y equals to minus 50x plus 40 in bracket 1 minus x. This you work out, we find y equals to minus 50x plus 40 minus 40x, meaning y equals to 40 minus 90x. This is our equation now. Now, this being a linear function, algebraically, it shows you that on the graph, this will be a straight line touching the y and the x-axis. And because it's a straight line, we don't require so many coordinates. We require only two coordinates, one for the one touching the y-axis, the other one touching the x-axis. So we can have this way. We can ask ourselves that if y is and x is. So assuming that we say if y is 0, if x is 0, sorry. If x is 0. If x is 0, then as we substitute 0 here, this will be a 0, and therefore y shall be 40. So y is going to be 40. And in case y is 0, if y is 0, then of course now this one, if we say 0, so we'll be having now 90x equals to 40. So our x shall be 40 divided by 90. So if y is 0, so we'll transfer this minus 90 on the left-hand side, so to become 90x, then divide by 40, and therefore we divide. So this will be 40 over 90. So 40 divided by 90. So on average, this will be 0.44. 0.44. That's how we can determine. And these are extreme coordinates on the y and the x axis. That's now when coh plays head. But again, in case coh, so when coh plays tail, when coh play tail, so we are going to have y equals to, look at now, if coh is going to play tail here, the values to coh to come out is 40 and minus 70. So this will be 40x plus minus 70 in bracket 1 minus x. When you work out, this will be y equals to 40x minus 70 plus 70x. Because of the sign, it will change to be to plus 70x. This shall give us y equals to 110x minus 70, and this becomes the second line. This being a linear function, then of course graphically it will be a straight line. So, and of course you can tell from the linear function, if this one has a negative gradient and this one has a positive gradient, then these two lines are going to crisscross. They're going to cross each other on the graph. So we are going to have here that if x is and if y is. So supposing x is 0. If x is 0, if we substitute x here, we substitute a 0, the whole of this becomes 0, and therefore y becomes minus 70. So this is going to be minus 70. That's y. And in case y is 0, then that means if you are to have this y substituted here, that y is 0, we'll transfer 70 this side. So we'll have here 70 equals to 110x. And therefore, x equals to 70 divided by 110. So this is going to give us, so this is 70 divided by 110. This is 0.664 on average, 64. So these are the two values, or the two coordinates on the y-x axis and on the y-axis. And therefore now we can be able to have the two lines on the Cartesian plane. Now how to develop the scale? Y-axis, the highest value of y is 40 and the lowest value is negative 70. That means we can be sure that we'll be having on the y-axis positive values and negative values. The x-axis, the highest is 0.64, the lowest is 0. So therefore we'll be having only on one side. So assuming that now this is my Cartesian plane, so we have this as the values. So we have this. So we draw a line. That's the line we have. And assuming that this being our y-axis, we can come up with a scale. So if we give a scale of, so let's say 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. See. So if this is now my 40, my 30, my 20, my 10, my 0, then minus 10, minus 20, minus 30, minus 40, minus 50, minus 60, and then minus 70. That's my y. Then x-axis we're having up to 0.64. So you can have this kind of a scale. So up to 6 there. So this is a scale for the x-axis. 1, 2, 3, 4, 5, 6. So this is my x-axis. If this is now my 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and 0.7. That is what we have. Now, this being my x and is my probability, then I connect. My first coordinate is 0 and 40, which is here, 0 and 40. And the other one is 0 and 0.44. Let's say 0.44 is here. So I draw a line touching the two. So the line touching the two. So we'll have this way. 40 and 44. 40 and 0.44. And 0.44. So this is my first line. My second line is this one with 0 and -70 here, -70. And you have the other one which is 0 and 64. So assume that my 64 is here. So I draw a line here. I draw a line. This is my line. That's my line. So I have the two lines. And if we are accurate, then of course we'll find that as we draw up here, this shall give us 0.55. The answer we found as the probability of Kamau playing head was 0.55 there. Then when you draw this way, we should get 9.5. So here, so you should get here the answer as minus 9.5 as we found as the value of the game. So graphically, we can show that the two lines are going to cross each other at 0.55 for the for the x-axis, and minus 9.5 approximately 10 there for the y-axis. That means Kamau is going to lose 9.5 shillings to Koech, and he's going to play 0.55 of the times. That is head and not the tail. That is all about the graphical methods. Now, I would want us also to make a conclusion concerning this zero-sum game using what we call a flow chart. This is a flow chart for zero-sum games. All what we have covered in lesson 4 and this lesson 5, then we can present it on a flow chart diagram in form of a DFD, data flow diagram. Now, the flow chart will begin here with a start. This is a start. Then the first action we did, especially for this question, Kamau question, we determined first of all we prepared the payoff matrix. That is an activity. An activity we normally use this box. So this is prepare payoff matrix for the game. That's the first activity. And then from there, we actually determined also whether there is saddle point. We tested whether there is saddle point. That one is not an action or is not an activity, but it is a decision. So here we determine whether there is saddle point. So we say, is there saddle point? Is a decision. So if yes, we'll have the game ending. And if no, then the game will proceed to the next stage. The next stage is where we determine whether the game can be dominated. And that is also not an action, but it is a decision. So we have here, we ask whether the game can be dominated. So can it be dominated? Can the game be dominated? This is actually a decision. And if yes, if the game can be dominated, then we just go ahead and dominate the game. So we say here, dominate the game. And after you dominate the game, we also still go back to step one here. We check whether the game we can have saddle points. So we say, is there? So is there saddle points? So is there saddle point? Is a decision. So we say if yes, then the game will end, of course, if yes. But if no, then of course it's just like the way we don't have domination here. If we cannot dominate, the way we solve the game is the same as if there's no saddle point, then of course we solve that way, this way. So here we have an action or an activity, which we say here that this is no. If no, we have an action. We say solve for mixed strategies. For mixed strategies. Something else again. If, for example, after you have solved for mixed strategy, then you just go to the value of the game. So you determine also is an activity. You determine the value of the game. This is a determine the value of the game. That is when you have solved for mixed strategies, you can determine the value of the game. But even if it is a pure strategy game, pure strategy here is pure strategy game, this is pure strategy game. So when you have pure, you can still come and determine the value of the game. So meaning this line will touch or will connect there. That way. This is determine the value of the game, even if it's pure. So this is for the mixed strategies. This is for the pure strategy game. Then the game ends. So here, the game will end. So the game will end here. This is stop. The game will end. Stop. Well, here the game was starting. So it was start. That way. You can have an arrow showing that where the arrow is going. That way. The rest of the arrows go sawa. That way. Now, this is what we call the flow chart diagram for zero-sum games. And we have done these games. A game where there was saddle point from the the word goal. So this is how we solve the game. A game where after no saddle point, we try to dominate. And we dominated, and we found there is saddle point, we ended the game. A game where there is no saddle point, it cannot be dominated like this one of Kamau and Koech, and then we solve from the mixed strategies, and then now finally we have the value of the game. This is what we call a data flow diagram for the zero-sum games. That is all. Now, the last game is called non-zero-sum games. Now, non-zero-sum games is just opposite of the zero-sum games we have covered. So you can indicate this way. Non-zero-sum games. Now, I had explained initially that non-zero-sum games are those games that the players, they may gain all of them, the players may lose all of them, or a player may gain while the other one is losing, but not necessarily that one player's gains are the same as the other player's losses. So these are called the non-zero-sum games. So where one player's gains are not necessarily the same as the other player's losses. And these are games that we would expect in business world, that companies will do business and they make profit, though they make profit differently, or they make loss and the loss is also different and all that. That's what we call the zero-sum games. Now, in business world, many competitive situations cannot be modeled as zero-sum games. And therefore, the players in zero-sum games, they may gain all of them, they may lose all of them, or one player gaining and the other one losing. Now, when it comes to these zero-sum games, we have some applications. So one application is prisoner's dilemma. Prisoner's dilemma. This is the most applied for the zero-sum games, prisoner's dilemma. Now here, we normally assume that two suspects, they are put into police custody and they are separated or so, and then the prosecutor confides to each, gives him the options, that you have an option of confessing for a crime that you have been accused, and you have an option of denying, not confessing. Now, in prisoner's dilemma, we normally assume we know the solution because of what we call the equilibrium. There is now what we call concept. So we have concept of equilibrium. Equilibrium. Now there are two concepts here. So we have Roman 1, we have what we call the efficient or Pareto equilibrium. Now, this efficient equilibrium or Pareto equilibrium is applicable to cooperative games. Cooperative or none, or not none, but cooperative or communication. Cooperative or communication games. Communication games. Communication games. Now, these communication games, we can say, are just like, let's say, negotiations. Negotiations. We can talk of, let's say, collusions. We can talk of coalition. We can talk of collective bargaining. Bargaining. We can talk of truce. That is peace talks. Such, these are examples. Now, this one is collective in nature. These are collective games where you work together for the value of the game. Now, this we call them as efficient or Pareto equilibrium. Now, that Pareto equilibrium is the outcome of such games. And we normally say that for the prisoner's dilemma, we normally say here that the not confess. This is, so not confess as in deny, is the efficient equilibrium. It's known that way, that as per the application, which is prisoner's dilemma, the not confess option or the deny option is the efficient equilibrium. These are games where both of you actually remain at the best position. You play unanimously. There are games where you play unanimously and you agree on what to play. That I've given even the applications of such kind of games. Then we have the other one, Roman 2, called Nash. Nash equilibrium. Equilibrium. Now, this Nash equilibrium is applicable to non-cooperative non-communication games. So these are applicable to non-cooperative or non-communication games. Now, these are games where you don't communicate, you don't agree, so you just play what you think will put you into a better position. Now, the application of this one are, we have, let's say, in fights, let's say in what you call strikes. We can have also the suspension. You can have expulsion, etc. Now, these ones are individualistic in nature. This is where you play on your own. You don't negotiate, you don't agree with the other player. Unlike these ones which are collective in nature. So this one you don't negotiate. And normally we say that the confess option is the Nash equilibrium. That's the outcome. The confess option of this game, of the prisoner's dilemma, is always the solution, which is the Nash equilibrium. So the key word, the key thing is that the efficient equilibriums are applicable to the communication games, while the Nash equilibrium are applicable to the non-cooperative games. I've given you the examples concerning the cooperative games and the examples concerning the non-cooperative games, and that is the position. So we'll have to do an illustration concerning the prisoner's dilemma to understand these concepts and the equilibrium we have. Now, the illustration concerning prisoner's dilemma, it reads that two suspects are taken into police custody and separated. The prosecutor is certain that they are guilty of a specific crime, but he does not have adequate evidence to convict them at trial. He points out to each suspect that each has two alternatives: to confess to the crime the police are sure that you have committed, or not to confess. If you both do not confess, the prosecutor states or will book them for minor charges where the jail term is 2 years in prison. Well, if you both confess, you'll be jailed for 8 years. You'll be jailed for 8 years. If one of you confesses and the other does not confess, the cooperative one will receive a lenient treatment of half a year or 6 months jail term, while the other receive the maximum jail term allowed by the law of 14 years. Now, required, find the optimal strategies for each player and the value of the game. End of question. Now, we want to advise on the outcome, although we already know, as per these equilibriums, we know the outcome, whether it is Nash equilibrium or it is efficient equilibrium. The first thing to do is to come up with a payoff matrix. So this is now going to be a payoff matrix. So a payoff matrix. So payoff matrix. This is still a two-person game. So always we have suspect 1 on the side, suspect 2 up there. So this is suspect 1 with a confess and deny here. We have suspect 2 with a confess and deny. This is confess and deny. Now, the different thing comparing the zero sum and non-zero sum is that for non-zero sum, since the gains of one is not the loss of the other, we normally record a pair. For example, you are told that if you both confess, as per the question, if you both confess, you'll be given 8 years jail term, meaning suspect 1 will go in for 8 years, suspect 2 will also go in for 8 years. So that is record a pair. If you both deny, you'll be booked in for minor charges where the jail term is 2 years each. 2 years each, that's what you are told. So suspect 1, 2 years, suspect 2, 2 years. If one of you denies and the other one confesses, the one confessing is going to get 6 months. 6 months is half a year. So let's say half. Well, the other one goes for 14 years. The one confessing half, the one denying goes for 14. If the one denying here goes for 14, the one confessing goes for half a year. That's how we're going to put it. So now our table or our matrix is complete. This is how we record for the non-zero sum games. But for zero sum games, remember you are recording only one value, which means there is a gain and is also a loss to the other player. Now, the solution to this one is we are going to assume here that in case it is cooperative game, if the two suspects are going to agree, they'll have the whole time with them to agree, to discuss. So they can agree not where one is denying, the other one is confessing. This is not possible. It's not fair. So they can only agree either they both confess to get equal jail term or they both deny to get equal jail term. But for denying is less a jail term than the confessing. And since this one is jail term, not profits, they'll want to minimize. And therefore you can say here that the deny option for both suspects is the efficient equilibrium. So the deny option for both suspects is the efficient equilibrium. That is already known, and that is where they can settle. But if number 2, if it is non-cooperative game, if it's a non-cooperative game, then it is difficult for us to agree on how one or they are going to both play. They are not going to agree anyway. They are not going to discuss, but the way they will play is as follows. We'll say here that if suspect 1 confess, suspect 2 will. So look at that. If suspect 1 confess, suspect 2 will do what? Let's see. Suspect 1 is here on the side, confess is here, meaning this is the first row I'm dealing with. Now, this being the first row, the suspect 2 jail term is the second place. Second place is suspect 2. Meaning, if he confesses, he gets 8 years. If he denies, he get 14 years. Suspect 2 is likely to confess to get 8. 8 is better than 14. So therefore, we'll confess. That become our solution. Then if suspect 1 deny, suspect 2 will, let's see. Suspect 1 on the side, deny. Suspect 2 will do what? If he confesses, he get half a year. If he denies, he get 2 years. Half a year is better than 2 years. So suspect 2 is likely to confess again. So confess. That tells you what? That suspect 2 will always confess, irrespective of what suspect 1 is going to do. He'll always confess. Then we also try for the other one. If suspect 2 confess, suspect 1 will. Let's now move to suspect 2. If suspect 2 up here confesses, meaning we have the first column, the suspect 1 values or jail term are the first place. So 8 and 14. Suspect 1 confessing get 8 years, denying get 14. So of course it's likely to confess to get 8 years. So here the answer is confess. He will always confess. But again here, if suspect 2 deny, suspect 1 will, let's see. If suspect 2 on top here is going to deny this second column, suspect 1 will get a half or 2, the first place, when he confess, when he denies. He is likely to confess is cheaper, is going to be 1/2 year than 2 years. So he's going to confess. Look at that again. Suspect 1 will always confess irrespective of what suspect 2 does. And therefore, we can make a conclusion that it is true that both suspects are going to confess, as we had given here, that confession option is the Nash. So you can say here that therefore the confess option for both suspects is the Nash equilibrium. That's what we expect. The confess option for both suspects is the Nash equilibrium, and that's how we can play such a game. Now, that one is prisoner's dilemma as one of the application. I can give another one, another one here, number 2, as let's say chicken and hawk games. Now, these chicken and hawk games is where a player is going to play tough, while the other one is going to play not tough. So we can say that one player is going to chicken out, and the other one is going to play tough. So this is in businesses. We can have a company taking the bold step of making a particular decision. Another company may not be that bold and therefore will not take such, and therefore we can call it as a chicken and hawk game. Now, the example I can give there is that two companies, I'm giving now illustration, two companies, so two companies, X and Y, are to produce and sell a product whose selling price is either shillings 10 or shillings 20. So two companies, X and Y, are to produce a product and sell it, and the price is shillings 10 and shillings 20. Then you say that the total demand is, we give it 1 million and 500,000 units for the two prices respectively. For the two prices respectively. Rules. The first rule is that if both companies sell at the same price, they share the demand equally. Then if one company sells at shillings 10 while the other sells at shillings 20, the company selling at shillings 10 sells for the entire demand. Then each company has a fixed cost of shillings 5 million. So required. So advise the companies on the prices to adopt. That's also a game that two companies X and Y are to produce and sell a product whose selling price is either shillings 10 or shillings 20. The total demand is 1,500,000 for the two prices respectively. Rules of the game is that one, if both companies sell the same price, they share the demand equally. If one company sells at shillings 10 while the other one sells at shillings 20, the company selling at shillings 10 sells for the entire demand, and each company has a fixed cost of shillings 5 million. This one is fixed cost of 5 million, whether or not you are producing or selling. Then required, advise the company on the selling price to adopt. Now, the solution here is that so if they sell at same price, then so the profit will be price, so revenue, that is revenue which is a PX minus cost, so it is fixed cost. So in our case, if they're selling at the same price, maybe like it is at a price of 20, so it is going to be price of 10, it will be 1 million each at 10, not at 10. We are sharing. They are sharing the demand. They are sharing. I told here that they're going to share the demand. So meaning each company will have 500,000 each at 10 minus 5M. So this, I better give you this way, half of 1 million units. That you can see, that 1 million units is for the price of 10 shillings. And then, or half of 500,000 at 20 shillings minus 5M. So this is each company. Now each company will have this. So each company will have the following. You will sell half of 1 million, which is 500 times 50 times 10, which is 5 million. 5 million. 5 million minus 5 million, you get a 0. And even if you sell at a higher price of 20, and you sell 500, so half of this is 250 times 20 is 5 million minus 5, you get 0. Meaning, if you decide to sell the same price, you will make a zero. Each of you make a zero. But in case, if they sell at different prices, now the one selling at the lowest price is going to sell everything. So there you can say here that profit will be 1 million each at 10 bob minus 5 million, while the other one, and the other one is only selling 0, so this is nil, at 20 minus 5 million. So the one selling at a lower price is going to sell everything. So therefore, it's going to make 10 million minus 5, you get to make 5 million. But the one selling at a price of 20, he sells nothing, but he's going to incur a fixed cost of 5, meaning he makes 5 million loss. So these are going to be my payoffs. These are my payoffs that if I want to come up with a table, I have this in my table. So I have now my conditional payoff, not conditional, but the game payoff matrix here. The game payoff matrix. So we'll have this way. This is company Y. So we have shillings 10, shillings 20, then shillings 10 and shillings 20 for the company A. No, company X, sorry. We have two companies, X and Y. Now this is my payoff matrix. We indicate if they play what, if they charge what price. So we have seen there that if they sell the same price, they make 0, 0. If they sell at a price of 10, all of them, they make 0, 0. Company X makes 0, company Y makes 0. If they sell the same price here, 2020, again they make 0 and then 0. But if they sell different prices, company X sells at 10, company Y sells at 20. The one selling at 10 will make a profit of 5 million, while the other one is going to make a loss of 5, so minus 5. The one selling at a higher price will make minus 5. The one making is selling at a lower is going to make 5. So look at that. This is going to be now our payoff matrix that we are having a case where we are making 0, 0 and we are making minus 5 and 5. So how do we solve this? So if it's a solution now here, solution, of course, this should be cooperative. So cooperative and then uncooperative. Now, if it's a cooperative game, what do you think will happen? Can we agree that one to make a negative, the other one to make a positive? It's not possible. We can only agree we sell at the same price, which is true. So we're going to say here that both companies will sell at same price. That's what we're going to agree. Same price, either 10, 10 or 10, 20 shillings. So same price, all of us. But if it is non-cooperative, this is non-cooperative game, then we look at the effect. If you sell at a lower price, you are likely to make a 0 or a 5 million. But if you sell at a higher price, you'll make negative, and it's evidence there. So a higher price has a particular risk of minus 5. So therefore, this one is both companies will sell at shillings 10, the lower price. This price has no loss. Either you make a 0 or you make 5 million. But the other one of 20 shillings, you will make either a 0 or you make minus 5. So therefore, everybody will want to avoid that. So everybody will sell at shillings 10. So that is another way of putting the same game, and it is still non-zero sum game. So that's all about that illustration. Chicken and hawk game, and the other one of the prisoner's dilemma. So last but not least is the applications. Where do we apply game theory now in totality? Where do you apply game theory? We can apply game theory in development of bidding tactics. Development of bidding tactics. So you want to bid, you want to put a price, and for this one you have to check what others are bidding so that you can fix a price that you are going to win. Then on is a collective bargaining. When you are doing some bargaining, the government, the trade unions, COTU, FKA, they have to apply this game theory. Pricing policies. So how you fix and put and maybe allocate or indicate the price of your products has also to do with the game theory, because other parties or other suppliers, they are also having the same product and they are pricing differently. So you have to also apply game theory there in pricing policies. In devising advertisement strategies. So how do you advertise? So a company advertises this way, you advertise differently so that you can capture many customers. So therefore, we can apply game theory there in advertising strategies. Next one is the time to introduce a new model or a new product in the market. This is now launching. When do you launch? Some companies, they may have a new product. They start selling the product before they launch the product, because they are timing the right time they can launch or unveil this new product. So those, among others, are application areas of game theory. And lastly, we have limitations of game theory. Limitations. Now, one of the limiting factor for game theory is incomplete or weak theoretical background, where some players do not know and others, they know more than the other players. Exactly, for example, they limit these cooperative games. The coalition, when one party knows more than the other. The collision, the negotiation, the collective bargaining becomes a problem if one player has a hidden card and the other. Therefore, we need to have open situation, and so that we can have all of us fairness. Another disadvantage or either limitation is the presence of the government. Now, government either as an active player or government as a referee or what you call arbitrator. Now, the government can be an active player, especially when it's offering the same services. The government has hospitals. The government has schools. So these are active participation in the market, that we are giving same product to the customers, and the customers have a choice. So you have to play what the government says. If the government says this is the curriculum, you also have to adapt the same. If the government give the dates for the exams, this is the dates you're going to follow. So that's how the government now comes into a game as an active player. Also, the government through the judiciary can come in and maybe arbitrate some of the cases that the government was not a party, but since now there's a problem between the two parties, they come to the government through the courts, and the judiciary or courts would dictate, and therefore that's another way of government getting into the game, which it was not part and parcel. Then number next is presence of trade unions. That's true. Between the workers and the company or the employer, we can have a trade union coming in, and when it comes in, the argument becomes different, and like when it would be employees of the company X and the company X management. But now when the union comes in, the game becomes somehow affected, either positively or negatively. Then the other one is the number of players is also a limiting factor. If the number of players increases, the game becomes complicated. We have been doing only two person, but if it's more than 2-person game, then that becomes again complicated. And the last one is the data availability, knowledge of the specific options of your opponent, and even these outcomes, like now knowing that the demand and the price and the cost put together, they will give us a loss or give us a profit. If that one is not known, then it's also not possible for us to play the game, because we're using these payoffs to play the game. If you don't know the outcome or don't know the options available to the other player, becomes an issue. So therefore, that again limits the game. And that is all about limitations of game theory. Now, we've come to the end of lesson 5, and it's also the end of this game theory as part and parcel of the decision theory. Now, this also is the end of the topic 7. Topic 7 was decision theory, where we have covered in 5 lessons, we have covered the 4 uncertainties, or the 4 environments: environment of certainty, environment of uncertainty, environment of risk, and environment of competition, which is now this game theory. That is also another area that you need to put more emphasis, because it is examinable, and you would say that it is an area that you can easily understand, but you have to put some exercise and put some more vigor towards this topic. Next, we'll go to the topic 8, which will be the budgeting and budgetary control. For now, have a nice time. Thank you.